Okay, good. Thank you so much for having me. Again, my name is Bryan Thomas. I am the station chief for the NOAA Atmospheric Baseline Observatory. There are 4 of them, and I'll be speaking about the measurements that we make, specifically the atmospheric measurements that we make. So, the beginning here, yeah, okay. Good. So the first picture here is our new site, an overview of our new site. And so you can see the tower. I'll just point out, we have the sampling tower of the radomes that have inside of them the satellite antenna. We have a really nice roof deck on that building in the middle of the picture. Those are some salient points. And then on the side of the driveway there, we have this nice science campaign platform where we can drop sea containers that are already all set up, and you can test them before they go out for deployment. There we go. Okay, so I remember from last time that this takes a minute. Okay, so here we are in relation to NARL. So you can see the blue one in the middle and the top, that's sort of NARL. You know where the airport is, and so the red star, that's where we are, inland and east. And the idea is that we want to be away from a lot of point sources of pollution because we want to monitor the background levels of the atmosphere. Okay, and this is a plan view, and it shows, again, the green square would be the sort of NARL area in the far left, and then you see out in the lagoon there and in the Arctic Ocean, that's where the predominant wind direction is. You can see on the windrows, it almost always comes from the east, almost all year. And we want that air to be well mixed, representative of the marine boundary layer, and we want to be able to say that we haven't seen any point sources of pollution in that air before it got to us. And if it comes from a different direction, then we factor it out. So we can tell when we take our flash samples, you can see here on the left, we can tell where that air has been for the last 10 days. And we know that it almost always comes to us around like that. From on the left, you would see that would be Siberia, and then it would come around and it would come from the east and come to us. That's a very typical profile or back trajectory of what we're measuring. And then on the right side, you can see there that with us in the middle, we would be able to see all around the circle where those possible point sources are, and we can factor those out so that from about 45 degrees to about 130 degrees, we have that constant wind almost all the time. And you notice the windrows shows us that's why we're there. We want to see that wind almost all the time. The NOAA, the National Oceanic and Atmospheric Administration, we're more of the A part of NOAA, the atmosphere part. And this is an example of our network taking the pulse of the planet. You may have seen this from Bryan yesterday during. I just want to reemphasize that we are one of the 4 observatories, the 4 baseline observatories, and then represented by the blue squares. And we have that nice line down the planet. And we can kind of see the atmosphere come across us. So we have the sort of 3 pillars of what we're doing. We're tracking the greenhouse gases. We're looking at the stratospheric ozone and specifically the recovery of that ozone layer that has had a hole over the Antarctic. And then we're also looking at the radiation, the solar radiation, the energy budget in the atmosphere. I'll quickly go through those. What are we doing here? We're looking at global pollutants, and specifically one I'll talk about is CFC-11, the chlorofluorocarbon that was used and was then banned in the Montreal Protocol, and what we've noticed from that. Then, of course, the ozone, which is what it affects. We want to watch for that. We want to watch that it's recovering as we expect. Then, of course, greenhouse gases like carbon dioxide and methane and water vapor, the ones we're familiar with, and then ones that might be less familiar, like nitrous oxide and sulfur hexafluoride, and where those come from and why, and even in very, very small amounts that they affect the atmosphere. Aerosols, solar energy, and soil temperature. What is that energy budget again? What's happening when the sun comes in? What happens in the atmosphere? And then what happens when the sun warms the surface? And what are those variables? And how do they change over time? That's what we're looking for, because we want to know what energy is available in the atmosphere for chemistry to happen. The magnetic field is a very important thing here so far north. With our partners in the USGS Geological Survey, we're monitoring the magnetic field all the time, and then once a week we go and we calibrate our observations with their continuous measurements so that they can adjust, see over time how is that magnetic field changing. Meteorology, so the Climate Reference Network, that's something that is all over the United States. We have a node here of the Climate Reference Network. So we have the standard measurements, standard instruments, and they get serviced, and we host those instruments, and they are an example of a standard that people can reference against when they're looking at meteorological data. And then, of course, we have the seismometer that's run by our partners at the Alaska Earthquake Center, and the global positioning system that's managed by our partners at UNAVCO. And those are long-term installations that are really important for looking at what else is going on besides just atmosphere. But we host them because they tell us something about the whole Earth system and the interaction. And they also are stable site, right? We're here for the long term, and we want to be able to host these things and be able to have a really long time series for all of these things. The satellite antenna is the same thing. We want to be really far north because orbiting satellites that we're watching, they're in the air, they're in the space over us more times because closer to the North Pole. So we get more data from those satellites than they would at a lower latitude. So again, just to look back at my first slide from a little bit of a different angle, we're kind of to the southeast here, and you can see in the horizon, that's the lagoon. That's Elson Lagoon. That's the Arctic Ocean. That's where that nice air comes from almost all the time. And our sampling tower, 90 feet, twice as high as the other one. We have the roof deck, we have the campaign deck, and we have a nice area around us to keep us from getting that point source of pollution. So, Arctic science, the Global Atmosphere Watch for the WMO, we are a global cryosphere watch station for the WMO. So we look at the snow, we look at the atmosphere, and we look at those in ways that are comparable across all those sites in the network. So we can compare directly to that data from our site. We have that 45-year, almost 50 record now of observations. We're co-located with the Department of Energy, Atmospheric Radiation Measurement, and as I also said, our partners at USGS, and we're very close to the Barrow Environmental Observatory. So we offer that place for very adjacent measurements, right? We have the meteorology, and we have the, for example, the things that are happening on the Barrow Environmental Observatory, they can be directly connected very closely to what's happening on our site. So we have about 225 climate variables that we're monitoring. And you can see some examples here. You can see on this one on the left, you can see there's carbon monoxide, carbon dioxide, isotopes of carbon, and then just plain carbon dioxide. So but you can see that they're being monitored all at the same time. So you can see the changes relative to the same time period, and you can draw conclusions from that. And in the middle there, there's the other Montreal Protocol gases, some of the other ones that we're interested in. We monitor many of those at parts per trillion levels, so very, very precise measurements. We can do that because we're constantly there. We have good power and cooling. So our gas chromatograph can be calibrated really often. It doesn't have to be moved in and out and have to be readjusted because it's always there. And here's an example, sort of what you saw from Bryan Vassell about the breathing of the planet, the pulse of the planet. You can see that breath in and breath out, and the seasonal changes of the carbon dioxide that we notice in North America, especially with the blue line. So this is sort of, again, demonstrating a strong time series that we can commit to trying to be there for the next 50 years to show what the time series is going to do. Here's an example that I really want to highlight about, again, CFC 11. This is a band compound under the Montreal Protocol. We're measuring it at parts per trillion on the left here on the vertical axis, and you can see the long time series, and you can see that we're expecting it to do a particular trajectory as it decays in the atmosphere, because it shouldn't have been added anymore after 2010. Well, what we saw is that in fact it did stop decaying. The dashed lines would be what we would expect, and then around 2010 we saw there was a bend. Right, there was some kind of enhancement that was happening that was not to expectations. So atmospheric baseline observatory measurements were so key to that, because we were there before, we were there during, and we were to show the transition and what happened. Because once it was detected, the Montreal Protocol kicked in, and everyone said, wait, this is happening, it's not supposed to happen. And guess what? Whoever was doing that, they had to change, and then we're seeing that there's a recovery. There's a recovery. So it's bending back down to where we're expecting it to be. Now, if we hadn't been able to monitor that, then we wouldn't have been able to recover to get back on the trajectory of the repair of the ozone hole. So that's a really important result that we were able to facilitate because of our location and our co-location, our location as part of the atmospheric baseline observatory network, and being able to show the time series, the before, the during, and the after the event. So we also, I mentioned before, the incoming solar radiation, the energy budget of the atmosphere. This is an example of something that we can do because we're here all the time. We're facilitating the Mosaic expedition, which you may have heard about, right? Freeze the icebreaker into the ice. Well, they also put out a lot of, on the ice, they put out a lot of stations, and they weren't going to be able to monitor them, manage those stations, go out and clean them all the time. Right. So before they did that, they wanted to see what's the best way to make sure that our radiation measurements are as clear as possible. Right. What do we do to keep the ice off these measurements, the instruments, for as much as possible? So I call this the bake off. Right. Put all the different ideas. And we were able to facilitate that because A, we already had some of these instruments in place. So we already had some ideas and some expertise about it. And B, because we had this stable place to do this, they could all be in the same place at the same time and overwinter and see what happened. And then when the Mosaic expedition went out, then we have that information to inform what instruments out there. And it made it more successful. They were able to get more data because they had this information first about how to keep those instruments clear of ice. Yes, I did. Thank you. It is hard. So these are some example ideas to help us think about how can we, as the NOAA Bureau Baseline Observatory, how can we help? We can ask questions like, how are aerosols changing with declining sea ice? That's something that we can't necessarily answer all by ourselves. We want to be able to connect with other Earth system scientists to help answer that question. Same thing, how can observing platforms and networks be connected in better ways? How can we be harmonized so we're gathering data that could be compared? Okay, thank you very much. I'll be available for questions.
And actually, thank you